Hi, in this lesson we're going to be looking at finding the eigenvalues and eigenvectors of a 3x3 matrix. In the previous lessons we've been looking at doing this with 2x2 matrices, and we've been sort of getting some sort of intuition about eigenvalues and eigenvectors by thinking about it in terms of transformations. And we looked at two-dimensional transformations and what the eigenvalues and eigenvectors are telling us. With a 3x3 matrix, we can kind of do this again and think about it in terms of transformations. If we go beyond this, because we can actually find eigenvalues and eigenvectors of larger matrices, larger square matrices, so 4x4, 5x5, etc. And obviously beyond this, it's very difficult to think of it geometrically at all. So we're just going to get a feel for what's going on. We've got this example here of a matrix that we want to find eigenvalues and eigenvectors in. So I'm going to treat this as a transformation matrix, and I'm just going to sort of have a look at what's going on with this. Right, so I've drawn a cube into here in AutoGraph, and what we're going to do now is we're going to apply the transformation matrix to this. So if I just select that and matrix transformation. Okay, and the matrix we've been looking at is, or we will be looking at, is this one. So 0, 2, 0, and 1, 3, 2. Okay, and what's going to happen is that this blue cube has been transformed in some way, and we're getting this kind of purple looking skewed transformed shape here. Okay, so what we're interested in is what's kind of gone on with this. Has it been kind of stretched and skewed, and what's actually happening with this? Right. Okay, if we remind ourselves of what we're trying to find, we're trying to find a vector that if I call this matrix M, I'm looking for a vector that when I multiply it by this matrix M, so we say that's my vector here, I'm going to get something that's going to be equal to a scalar multiple of that vector, and that is what it would make an eigenvector. So and what we've done in previous lessons, we've looked at how we can rearrange this, and we end up with this here. Okay, so what we're looking for is we're looking to solve this particular equation here. I know what M is because I've got it over here. So I need to work out what lambda is, which is what the eigenvalues are, and what V is, which is what the eigenvector is. So I'm just going to write this out in full over here. We've got 2, negative 1, 1, 0, 2, 0, 1, 3, 2. And I'm going to take away lambda I, so that's going to be and that multiplied by x, y, z is going to give me this here. Okay, so again, this is going to be our eigenvector, and lambda are going to be our eigenvalues. Now I can simplify this over here, and I usually would skip this step, and I would usually just write down this here. And this is the equation that we're looking to solve. Right, so what we want to happen is we want the determinant of this to be 0, because we need this to be singular, because we don't want there to be an inverse matrix that exists for this. So I'm now going to use that idea to give me what's going to be called my characteristic equation. So I want this bit here, the determinant of this bit here, I should say. I want that to be equal to 0 because I want this to be singular. Okay, so from this now, I'm going to form I'm going to be able to solve this. So I'm going to just simplify this. So that's going to be plus 1 times the determinant of that there. And what's the determinant of that there? And I want that to be equal to 0, brackets around there. Okay, so I now need to expand this, so 2 take away lambda, and this bit here is going to be 2 take away lambda squared, so I'm just going to write this as 2 take away lambda cubed, and then I've got plus, and this here is just going to be, the determinant of this is going to be 0, so I'll ignore that bit, and then I've got the determinant of this bit, which is going to be 0 take away 2 minus lambda, so it's going to be take away, I need to be careful, that there, and that's going to be equal to 0. Right, so what I'm now going to do is I'm going to factorise, so I'm going to expand it and factorise it. So you might want to have a go at doing that yourself, but I'm just going to write down the solution to this. We should end up with 2 take away lambda, lambda take away 1, and lambda take away 3 is equal to 0. Okay, so that tells me, if I just tidy up my work, I'm going to have 3 eigenvalues, 1, 2, and 3. Okay, so I've got lambda is going to be equal to 1, okay, and I'm just going to come over here now. Right, so one of my eigenvalues is 1, the other one's 2, and the other one's 3. So that tells me that because one of my eigenvalues is 1, that tells me that there's going to be a line of invariant points somewhere. So there's going to be a line somewhere where all of the points on that line are going to map back onto themselves. And this tells me that there's going to be a line that's going to be stretching 2 away, and this one's going to be stretching 3 away. Okay, so coming back over here, I'm now, because I know what lambda is, I could substitute each case into this equation here to find out what the corresponding eigenvectors are. Oops, sorry, that was my phone. Okay, so that's what we're going to do. So for when lambda is equal to when lambda is equal to 1, then I can put 1 into this equation here, so that's going to be 1, 0, 1, negative 1, 1, 3, and 1, 0, 1. Okay, so now from here I've got 1x plus 0y plus 1z is equal to 0, and I've also got negative x plus y plus 3z is equal to 0, and 1x plus 0y plus 1z is equal to 0 again. Okay, so using that, I know that x plus z has got to be equal to 0, and I've got a negative x plus y plus 3z is going to be equal to 0. Well, that tells me that x and z need to be equal and of opposite signs to each other. So I'm going to choose x to be 1, and I'm going to choose z to be negative 1, my eigenvector. Now if x is 1 and z is negative 1, then that's going to be negative 1 plus 3, take away 3 even, which is going to be negative 4. So that tells me that the y, in order to make this 0, would have to be 4. So that's going to be one of my eigenvectors. Now if I come over here and we'll look at another case, we'll look at when lambda is equal to 2. So that's the corresponding, so we'll call this E1, that's lambda 1. Okay, so for the second value, for our second eigenvalue, which is 2, I'm going to substitute it back into here again. So this time I'm going to get 0, negative 1, 1, 0, 0, 0, and 1, 3, 0. Okay, so this time, well, if we have a look at the top row, I've got 0x plus 0y plus z is equal to 0. So that tells me that z must be equal to 0. If 0x plus 0y plus z is equal to 0, so that means z is equal to 0. I've also got over here, if we have a look at the bottom row, I've got x plus 0y plus 0z is equal to 0. So that means x must be equal to 0. Okay, and if x is equal to 0 and z is equal to 0, I've got 0 plus 0y plus 0 is equal to 0. That means y can take any value that I choose, yeah, and because I've got a line of zeros here, that kind of tells me that y can be any value that I choose. So I'm just going to choose y to be 1. I can choose it to be anything. So my second eigenvector is going to be 0, and y is 1, and z is 0, so it's going to be 0, 1, 0. Okay, and for the third eigenvalue, so this is where it is equal to 3, and again I'm going to stick those into there, so I've got minus 1, 0, 1, I've got and this is the equation we're trying to solve this time. Okay, so I've got, and I'll write down my equations. Yeah, so I've got a negative x plus 0y plus z is going to be equal to 0. I've got a negative x, take away y plus 3z is equal to 0, and I've got x take away z is going to be equal to 0. So from this you may be able to spot that x and z have to be the same value. Yeah, x and z all have to be the same value. So I'm going to choose x to be 1 and z to be 1. Okay, and if x is 1, so that's negative 1 plus 3z, which is 2. So 2 take away y is equal to 0, so the y must be 2. Let's check that works. So negative 1 take away 2, negative 3 plus 3 makes 0, and this satisfies all of those equations there. So my third eigenvalue is going to be, underline these factors. Okay, so my third eigenvalue, eigenvector is going to be 1, 2, 1. Okay, so if you have a look at this, I've got my eigenvalue over here. Let's look. Okay, so when lambda is equal to 1, that's the corresponding eigenvector. And this one corresponds to this one over here. And this one corresponds to this one over here. Okay, so what this is actually saying is that I've got a line of invariant points here, 1 for negative 1. So anything along this line here, when it gets transformed, is going to map back onto itself. Anything along this line here is going to end up twice, it's going to be stretched by a factor of 2 further along in that direction, and anything along this line here is going to be stretched by a factor of 3 in that direction. Okay, thanks very much for joining me today. I look forward to seeing you again soon.